changing transformer. Auto transformer is a single winding transformer. Its primary and secondary windings are the same winding. One side is taken as primary, and by tapping the a portion of number of turns as a secondary. For example, if you want to, mainly it is used in generating stations and substations. For example, if we are transmitting a voltage of 400 kV level, we have to maintain that 400 kV on the transmission line. The transmission line voltage should be always constant. Then only it will be a stable transmission system. So to maintain that, maybe this 400 kV, that transmission line have some resistance and inductances or impedances, and there will be a current and voltage angle will be there, phi. So we have to consider R plus Jx quantity of impedance and also a current in the transmission line system. So it will maybe reduced into that 400 kV voltage level to a 380 kV voltage level. So that will be undesirable. So we have to maintain that constant voltage by changing the tap from tap 1 or tap 2 or tap 3. By changing the number of turns in secondary, we can make some modification or small level modification in the voltage level in the secondary winding of which is used in generating stations and substations for maintaining the voltage level. So auto transformer is also known as gap changing transformer. Okay, another classification which is based on the use in domestic, either which is used in domestic or transmission or distribution. We already said that there are two classifications. Single phase. Single phase is normally represented as 1, 5. Okay. Electrically we represent single phase as 1, 5 and 3 phase as 3, 5. Okay. So in our classes we may represent like that. Single phase by 1, 5 and 3, 5. Just the 3 phase as 3, 5. Okay. Then single phase transformers are used in domestic purposes. Okay. We already told the step down transformers are used in domestic purpose, which is normally single phase transformers. And transmission and distribution systems we use 3-phase transformers. Okay. So these are the another classification. And another classification based on construction, there are two types. One is core type. Core. Based on construction, transformers are classified into two: core type and shell type. Shell type. Okay. Core type and shell type. In core type, I can represent the lamination. We have already told to reduce the hysteresis loss or eddy current loss. Sorry, not for hysteresis loss. To reduce the eddy current loss, we made the core, conducting ferromagnetic core into laminations. So I hereby representing the lamination of a core. So number of laminations are sticking together to produce a full core. So here usually we constructed the core as C-shaped core, and which is closed, that magnetic circuit is closed by one straight rod. Okay, so there are actually two-piece cores. One is in C-shaped and another a straight bar, and which is sticking together. And the winding is placed on these two links. The primary winding is placed on this link, and the secondary winding is placed on this link. Okay, this is the core type. What is core type transformer? Constructionally, we are making a C-shaped lamination. So, numerous lamination in the C-shape, which is stick together, and in between these lamination, we use insulations like a mica or paper varnish. Okay. So this air gap does not exist to continue, because there is no air gap between this straight bar and this one. One lamination will place like this, and in another, the second lamination, the C shape will be at the downside and the straight bar at the upside. And under this lamination, alternately we place another one in this manner. I think you may understood that upper lamination will be like this. In below that we place in alternative manner, and that, under that we alternatively place like this. So why we are choosing the C shape? Because to get to wound the coil constructionally, we wound the coil to the core first, then we close that transformer core in as a closed magnetic circuit. We can't wind because the winding is very heavy. ഈ ട്രാൻസ്ഫോമറിലെ കോയിലിനായിരിക്കും വെയിറ്റ് കൂടുതൽ. സോ കോർ ലാമിനേഷൻസിന് മൊത്തത്തിലൊരു കോറായിട്ട് നമ്മൾ കൺസ്ട്രക്ട് ചെയ്യുമ്പോൾ ഈ സി ഷേപ്പ് കോറിലാണ് നമ്മൾ വൈൻഡിങ്ങിനെ വൗണ്ട് ചെയ്യുന്നത്. ദെൻ വി ക്ലോസ് ദ മാഗ്നറ്റിക് കോർ, എന്നിട്ട് ക്ലോസ് ചെയ്യുള്ളൂ. അതിന് വേണ്ടിയാണ് ഈ 2 പീസസ് ആയിട്ട് നമ്മൾ കൺസ്ട്രക്ട് ചെയ്യുന്നത്. Because we are constructing this as C-shaped and one straight bar. First we wound this winding on these 2 limbs. Actually we are putting that coil as a ring which we are placed into our fingers like that. We are putting coils into these 2 limbs, then we close this magnetic circuit. To get a closed magnetic circuit, we are placing another straight rod here, then close that magnetic circuit. The procedure of that construction is like that. First we are taking our C-shaped core, then we place the winding, then close the magnetic circuit by using that straight rod. Okay, and one second. Okay, so here the reluctance is very high because you can see the magnetic path is only, ferromagnetic material is only like this, only through this. Other major part of the windings will be placed at the air itself. The core is surrounding by air, so the magnetic flux lines in these path only. You can see if the magnetic flux lines pass through these side, our major part of this will be passed through our magnetic circuit, ferromagnetic core. But here most of the part in this side will be, flux lines will be passed through the air, so there will be some leakage. Leakage is more in core type transformer, so reluctance will be very high, and in either side surrounding with air. The core, in core type transformer, either side of the winding is surrounding with air, so leakage flux is very high. What is leakage flux? The flux which is not useful by the load or to produce induced EMF, which is not useful, thus lost as the flux lines which pass through the air is usually called it as leakage flux. എയറിലൂടെ പാസ് ചെയ്ത് പോകുന്ന ഫ്ലക്സ് ലൈൻസിനെയാണ് നമ്മൾ ലീക്കേജ് ഫ്ലക്സ് എന്ന് പറയുന്നത്. അതൊരിക്കലും നമുക്ക് യൂസ് ചെയ്യാൻ പറ്റില്ല, അതൊരു ലോസ് ആണ്. അതുകൊണ്ട് ആ ഒരു പാർട്ടിനെ ലീക്കേജ് ഫ്ലക്സ് എന്ന് പറയും. അപ്പോൾ ഈ കോർ ടൈപ്പ് മെറ്റീരിയലിൽ ലീക്കേജ് ഫ്ലക്സ് കൂടുതലായിരിക്കും, അതുകൊണ്ട് തന്നെ അതിന്റെ റിലക്റ്റൻസും ഹൈ ആയിരിക്കും. നെക്സ്റ്റ് വൺ is ഷെൽ ടൈപ്പ് ട്രാൻസ്ഫോമർ. ഷെൽ ടൈപ്പ് ട്രാൻസ്ഫോമർ is constructed as like this, as a E-shaped lamination. Which is okay, it is constructed as E-shaped lamination. Core is constructed as E-shaped lamination, then it is closed, that magnetic circuit is closed by a straight rod like this, and the windings is placed by both the primary winding and the secondary winding is placed on these 2 on only one limb. Okay, so the winding is placed here. Okay, so both the primary and secondary windings are placed in the middle limb of the shell type transformer. So you can see most of the flux lines will pass through the core itself. So we can say the reluctance is low and it is more expensive also. To constructionally shell type is more expensive, but most of the flux lines will pass through the magnetic circuit, ferromagnetic circuit core itself. So reluctance is low as compared to core type transformer. So based on construction, there are two type of transformers: core type transformer and shell type transformer. Core type transformer is like this, a C-shaped limb which is closed by a straight rod. In shell type, it is an E-shaped limb which is closed by a straight rod here. And normally this silicon steel is used as a magnetic core. Silicon steel lamination. These stampings, we call it as stampings, which is of 0.3 to 0.5 mm thickness. 0.3 to 0.5 mm thickness. Each lamination will have 0.3 to 0.5 mm thickness. And we already tell that, we say that transformers are very heavy. Mainly windings are very heavy. So in single phase transformers or three phase transformers, both are heavy. You may know that three phase transformer will have 3 windings, so it becomes more heavier than single phase transformer. But the transportation of a constructed transformer will be very difficult. So usually three phase transformers are not constructed in a single limb, because we can't transport that transformer from one place to another. Normally the transformers are constructed in some plants. For example, there will be a transformer construction plant in BHEL, Bhopal. But we have to consider the transportation also. The constructed transformer have to transfer either into some generating stations or substations. We have to transfer the whole device into another place through any transportation method, either by railway or either by road. So we have to rebuild the road or railway to withstand that much heavier device in a transportation system. For that, in BHEL Bhopal, they reinforced the road to transport their transformers. Okay. So ഭോപ്പാലിലൊക്കെ അവരുടെ rail or road transportation ഒക്കെ reinforce ചെയ്തു to transfer that transformers from one place to another place. So that much heavier device ആണ് transformer എന്ന് പറയുന്നത്. So transformer transport ചെയ്യുക എന്ന് പറയുന്നത് ഒരു very difficult process ആണ്. So normally the transformers are made as single phase transformer. Three phase transformer ആണ്, but three phase transformers are usually constructed in a single, usually it will not constructed in a single core. Because of this issue of transportation, we make the transformers as three number of single phase transformers. Single phase transformer ആയിട്ടാണ് നമ്മൾ അതിനെ construct ചെയ്യുന്നത്. And we connect it either in star connection or in delta connection. 3 single phase transformers are constructed and we connect either in star connection or delta connection. Okay, star connection എന്ന് പറയുന്നത് ഇതാണ്. ഇതൊക്കെ നമുക്ക് പഠിക്കാനുണ്ട്. Star and this one delta, or maybe you have studied in your classes. 3 phases are either connected in star or delta. Okay, delta connection. So due to the transportation difficulties, normally three phase transformers are constructed as 3 single phase transformers which are either connected in star or delta configuration. Okay, so ഇത്രയാണ് core type and shell type construction transformers എന്ന് പറയുന്നത്. Then I am just explaining the schematic diagram of a single phase transformer. Okay, schematic diagram. Schematic diagram means it is an electrical representation of a single phase transformer. Schematic diagram of a single phase transformer. We know that for a single phase transformer, it have 2 windings. So I am not here representing the core, only the windings. It's for representing the core, I will put 2 lines vertically here. Normally we represent in schematic diagram core by 2 lines, and another winding is secondary winding. Conceptually, in a transformer there are 2 windings. One is called as primary winding, which is denoted like this, and the secondary winding is this. Okay, so there are primary winding and secondary winding. We know that the function of transformer is to transfer electrical energy from one electrical circuit to another one. So we are giving a voltage V1 in this terminal on the primary winding. V1 is applied on the primary winding, and the voltage at this terminal is, we take it as V2. Okay. So to establish a flux in the core, that means how to transfer the electrical energy from one circuit to another only through the magnetic means. So we have to establish flux on the transformer. So to establish a flux in the core, a minimum current is needed. So by applying a voltage V1, there will be a current flow which normally we written as I0, because we have not connected any load in the secondary. The secondary side is now open. So we consider the current as no load current I0. Okay. So to establish a flux on this, flux on this core, a minimum current is needed. So to produce a flux phi, here, phi is normally sinusoidal flux, so we can written as phi m sin omega t to represent a sinusoidal flux, which is maximum flux phi m sin omega t. Okay, phi m sin omega t is the flux produced in the primary winding. Okay, the flux linking with the primary, which is normally linked with the secondary also. The flux lines also linked with the secondary also. Okay, so according to Faraday's law, we know that whenever there is we are applying an alternating voltage, so whenever there is a rate of change of flux is there will be an induced EMF. A self-induced EMF will be produced in the primary winding, which is E1, and due to this mutually induced EMF, that is an EMF induced in the secondary, is E2. Okay, so whenever there is an induced EMF, whenever there is a rate of change of flux occurring in a winding, it will produce an induced EMF in the winding. So induced EMF in the primary winding is equal to d phi by dt, rate of change of flux. According to Faraday's law, whenever there is a rate of change of flux, an EMF is induced in the winding in the primary winding will induce in the EMF on E1. Here it is E2. Okay, so induced EMF can be represented as induced EMF is equal to, and then induced EMF is equal to d phi by dt. Rate of change of flux, we already known it as phi m sin omega t. This is the rate of change of flux produced in our winding. So RMS value of induced EMF, we can write the RMS value of induced EMF, E RMS equal to what? E RMS is equal to this phi m sin omega t. D phi by dt, that means we know that the value of phi, that is phi m sin omega t. So d by dt of phi m sin omega t and differential of phi m sin omega t is, which is equal to phi m into omega cos omega t. So we can write it as phi m into omega cos omega t. മനസ്സിലായോ നിങ്ങൾക്ക്? omega t. Okay. അതായത് induced EMF, according to Faraday's law, induced EMF is what? Induced EMF is d phi by dt. Then we know the value of phi is phi m sin omega t. Substitute phi m sin omega t in this equation, d by dt of phi. So you will get differential of phi m sin omega t is phi m omega into cos omega t. So we can write the ERMS equation as, RMS value of EMF equation എന്തായിരിക്കും? phi m omega cos omega t divided by, sorry, omega t is written here, and which is divided by root 2 will give the RMS value. So ERMS value. ERMS can be written as phi. Omega can be written as 2 pi f. So 2 pi f phi m into 2 pi f cos omega t divided by root 2. So we can do 2 pi f by root 2. Phi m into 2 pi f by root 2. Okay. So this is the equation for RMS value of induced EMF. Okay. So this value is 4.44 into f into phi m. Okay. So induced EMF of a transformer equation is E is equal to, we can written it as ET. Okay. This is a schematic diagram of a single phase transformer. It consists of primary winding and secondary winding. So we are applying a voltage V1 on this primary winding. It will induce an EMF E1 in the primary winding by a flux. നമ്മൾ ഒരു voltage apply ആണ് primary winding. V1 എന്ന് പറഞ്ഞ ഒരു voltage കൊടുക്കുകയാണ്. That voltage will produce a flux phi in the primary winding. That flux will be linked. That is an alternating flux. So according to Faraday's law, if there is a rate of change of flux, it induces an EMF in that winding, and also if there is any nearby winding, by mutual induction there will be another induced EMF, mutual induced EMF. So self-induced EMF of a primary winding എന്ന് പറയുന്നതാണ് E1. Mutually induced EMF produced in the secondary winding is the E2. Okay, so E1 and E2 is the. So we can write the equation for induced EMF either E1 or E2. We are writing the equation generally induced EMF as by according to Faraday's law, it is rate of change of flux d phi by dt. So we consider flux is a sinusoidal flux. Phi is equal to phi m sin of omega t. Substitute this equation on the rate of change of flux. That d phi by dt will get phi m omega cos omega t. Then RMS value, we are just considering the RMS value of the induced EMF, that is ERMS is equal to phi m omega into cos omega t by root 2. RMS value കിട്ടാൻ നമ്മൾ divided by root 2 ചെയ്യാണ് ചെയ്യുക. Root means square value. Okay, so phi m into 2 pi f by root 2 will give the RMS value of induced EMF. By calculating, it is 4.44 f into phi m. That is the frequency. Phi m is the maximum flux. So this is the equation for induced EMF. Okay. Then we can write induced EMF as RMS value of induced EMF E as what? Yes, 4.44 f into phi m. Okay, phi m, f into phi m. If we talk about one single turn, one turn or a single turn, rate of induced EMF is d phi by dt. But if we talk about the n number of turns as a primary winding, ഒരു single turn ആണെങ്കിൽ നമുക്ക് പറയാം rate of change of flux എന്ന് പറയുന്നത് E ആണെന്ന്. പക്ഷേ if we talk about the n number of turns, we have to consider the number of turns also. N turns, the induced EMF is n into d phi by dt ആണ്. Okay, so we have to consider the number of turns also. So voltage induced in primary winding, voltage induced in primary winding ആണെങ്കിൽ നമ്മൾ എങ്ങനെ കൺസിഡർ ചെയ്യുക, which is call it as E1. So E1 is equal to, we take the primary winding number of turns as N1. So N1 into ET. ET is the terminal voltage. ET, just represent ET as the rate of change of induced EMF. So if the voltage induced in secondary is considered, E2 is equal to number of turns in secondary is taken as N2 into ET. Okay, so here we consider number of turns in primary is N1 and number of turns in secondary is N2. Then we get E1 is equal to, induced EMF in the primary is ET into voltage induced in primary into N1, and the voltage induced in secondary winding is taken as E2 is equal to ET into N2. Okay. So we can written as, from this equation we can written as, therefore V1 by V2 is equal to E1 by E2. Okay. So we can write V1 by V2 is equal to N1, E1 by E2 if there is no load, and also we can write as V1 by V2 as equal to number of turns, N1 by N2. Okay. From this equation, induced EMF E1, which is equivalent to induced EMF or terminal voltage V1, we are taking, there is no loss because there is no load, so we take it as E1. E1 is equal to N1 ET and E2 is equal to N2. So we can say V1 by V2 is equal to N1 by N2. Okay. So just we consider a transformer. We already told core type transformer. Okay. We consider a transformer core and we wind a primary winding on this limb and another secondary winding on this limb. Okay. And V1 is the voltage applied on this primary winding and V2 is the voltage applied on the secondary winding. When secondary winding is open, what the current drawn by the primary winding? We normally take it as I0, no load current, because here there is no load in the secondary winding. നമ്മൾ പ്രത്യേകിച്ച് ഇതിൽ പ്രൊഡ്യൂസ് ചെയ്യുന്ന കറണ്ടിന് ഒരു ലോഡിലോട്ടും കണക്ട് ചെയ്തിട്ടില്ല. ട്രാൻസ്ഫോമർ പ്രൈമറി വൈൻഡിങ്ങിൽ ഒരു വോൾട്ടേജ് കൊടുത്തു, സെക്കൻഡറിയിൽ ഒരു വോൾട്ടേജ് പ്രൊഡ്യൂസ് ചെയ്തു, but we are not using that voltage. This secondary side is open. ഈ ഓപ്പൺ ആയിരിക്കുന്ന സമയത്ത് പ്രൈമറി വൈൻഡിങ്ങിൽ പ്രൊഡ്യൂസ് ചെയ്യുന്ന കറണ്ട് എന്തിനാണ് യൂസ് ചെയ്യുന്നത്? That current drawn by the transformer at no load is only used to magnetize the core. Okay, to magnetizing current. So we call it as magnetizing current and represented as I0. Okay, I0 is the no load current. I0 is no load current. We call it as no load current. Okay, no load current എന്നാണ് നമ്മൾ അതിനെ പറയാം, I0. Okay, so I0 is the no load current. It will be very a large value. When it is when we are connecting a load on the secondary. Okay, now we are going to connect a load on the secondary. I hereby representing the primary winding and the secondary winding here, and we are connecting a load here. Okay, this one is the load connected on secondary. Okay, when we connect a load on the secondary, what happens? It will be a closed circuit, so a current will flow through the secondary, written as, we represent it as I2. Okay, when there is a current, when it is drawing a current I2, essentially it will be establish a flux, another flux. When a coil flows, which carrying a current I2, it will produce another flux on this circuit. So there will be another flux produced on the secondary winding, and which will opposes the primary flux on it. Normally, the produced by Lenz's law, the change produced in the secondary winding will opposes the cause which produces it. So when there is a current in the secondary, it will produce an MMF on the secondary. A flux will be produced in the secondary due to the current I2. So that MMF will try to kill the flux on the primary, original flux in a killing instrument. It will try to reduce the flux because it opposes the primary flux. So the secondary flux will try to oppose the original flux and it will collapse the primary flux and it try to stop the transformer action. Okay, but that is not desirable, but the transformer will try to nullify that MMF. Okay, so we know that I0, we know that the V1 is the terminal voltage given to primary winding. It is approximately equal to the induced EMF E1. Now if the flux collapses, what happens? E1 will be almost equal to 0. If the secondary flux MMF try to collapse our primary original flux, E1 becomes 0. Then I0, we know the equation for I0, the no load current will be the terminal voltage V1 minus E1 by the impedance of the primary winding. So if E1 turns to 0, this I0 becomes large. Try to be a large value exactly equal to secondary ampere turn MMF. So it will try to nullify the change in the secondary, that is I2 and 2. So MMF in primary is I1 into N1, which is equal to, it is trying to produce a MMF equivalent to I2, N2. Okay, I2, N2. Okay, that means I1 N1 is the current which is established in the primary winding, which is trying to nullify the MMF produced in the secondary winding. I2 N2 is the MMF produced in the secondary. So secondary current I2 will try to kill the original flux, and the primary MMF produced I1N1 will MMF, that is the MMF in the primary, will try to nullify the effect of secondary current I2. So primary MMF and secondary MMF will be always equal but in opposite direction. So I1 will be large to nullify the effect of ampere turn balance. So this is the ampere turn balance in the transformer. നമ്മൾ സെക്കൻഡറിയിൽ പ്രൊഡ്യൂസ് ചെയ്ത കറണ്ട് കാരണം ഉള്ള എഫക്റ്റിനെ നള്ളിഫൈ ചെയ്യാൻ വേണ്ടി പ്രൊഡ്യൂസ് ചെയ്യുന്ന എക്സ്ട്രാ മാഗ്നറ്റിക് ഫ്ലക്സ് ഇൻ പ്രൈമറി ആണ് I1 N1 എന്ന് പറയുന്നത്. ഓക്കെ, സോ it will produce another flux I1 N1. Okay, so I1 will be the large current produced in the, so normally in this transformer we have considered a transformer. Okay, V1 is the primary voltage, and the current, initially it is the current, no load current I0, which is open, and when a load is connected here, there will be a current flow I2 due to, initially there is a flux line, that is phi, magnetizing flux phi m produced by the current flowing in the primary. When current starts flowing in the secondary winding, another flux will come in action, that is phi 2. So it will try to nullify or reduce, collapse the phi m. So it has to produce another current I1. It will be larger than I0. So it will try to, so this is the number of turn in primary and this is the number of turn in secondary. So N1 and N2 are the number of turns, and I0 will change it into I1 when it is I1 when it is loaded. Okay, so this is the magnetizing current is I0. When the load is connected, the primary current will be increased to I1. So I1 N1 should be equal to I2 N2. If any type of transformer we used, if it is auto transformer or distribution transformer or transmission type transformer, power transformer, this configuration I1 N1 is equal to I2 N2 is valid. So we can write it as V1 by V2 is equal to N1 by N2 is equal to I2 by I1. We can write it as I2 by I1. Okay, so we can write the EMF equation like this. Thank you.